Hi everyone. Today I would like to talk about properties of estimators. So in the last couple of lectures, I spent some time talking about the first lecture talking about Bayesian versus frequentist estimation. Then we talk about map versus ML. Then we talk about series of videos for MMSC, part 1, part 2, part 3, part 4. In linear MMSC, we talk about how to solve MMSC in general using conditional expectation. Then we actually talk about the goal and objective behind the MMSC. Then later on, we talk about the least square. I introduced 3 different ways for first time actually how to solve a least square problem. Then in the last video, I talked about the Bayes estimator, which is a general class of Bayesian estimation that you see that I showed that the MMSC, a map, and least absolute criterion are just a special class of Bayes estimator. Today, I would like to talk about the properties of estimator. How do you compare the estimator? How do you know one estimator is better than the other one? How do you get some statistics about the estimator that you have? Okay, so let's start. The first property that I want to talk about is bias. You all have heard this term a lot in different literature. This estimator is unbiased. This estimator is biased. Well, what does bias mean? So before that, let me just introduce, let theta hat be the estimator for a parameter theta. Okay, let theta hat be the estimator for parameter theta. Now we move here, bias. Bias of an estimator is defined, let me define it as a B of theta hat is equal to expected value of theta hat minus theta. So expected value of the estimator minus the true value. The true value, expected value of the mean of the estimator. Great. Now you might want to say, why expected value? Remember that theta hat can be a random variable. If theta hat is a random variable, then it has expected value. Okay, so this is called the bias. Now when you are talking, you see that it's a random variable is unbiased, right? What do they talk about that? This means unbiased random variable, unbiased estimator means P of theta hat is equal to 0. Therefore, is equal to this. So expected value of the estimator is equal to the true parameter. That's what the bias is. Okay, good. Now let's go to another one. Cramer Rao lower bound, or Cramer Rao, sometimes they call that CRLB. So what is CRLB? CRLB is defined as follows. Mathematically, first is defined as this: 1 over negative expected value of from the square means second derivative of P of x given theta respect to theta, right? Great. What is this one? Let's just define these terms here a little bit. This one is log likelihood. Second derivative of log likelihood, right? Then take expected value of that and 1 over that. Negate that 1 over that. It's going to be Cramer Rao lower bound. Why do they call that Cramer Rao lower bound? CRLB is the lower bound for the variance of an estimator. Lower bound for the variance of estimator, for the variance of the estimator. So an estimator can have a variance as low as CRLV. It cannot get lower than that, right? It's a lower bound for the variance of estimator. So estimator can have a variance lower than CRLV. Good. Mathematically, it means this. Okay, so this means that the F sigma theta hat square, the variance of this is greater than or equal to CRLV. Great. So that's for CRLV. Okay, so that's CRLV. Now, the next one I want to talk about, next property is the, consistency. Consistency. So consistency of an estimator is defined as follows. It says that the theta hat, the estimator, will converge in distribution. Remember in conversion probability to the true parameter as n goes to infinity. In other words, as the size of a sample size increases, the estimator is going to be more concentrated toward the true parameter. Okay, so this is very different from the bias. Usually people make this mistake in literature. Bias means that the expected value of estimator converges is equal to actual true parameter. But the consistency says that the parameter, as n goes to infinity, as sample size increases, size of sample size increases, converges in probability to the true parameter. Okay, so let's write it down. As sample size increases, the estimator converges the true parameter in probability. Good. Okay, so that was consistency, which is also different from bias. Now, there is a term here that I would like you to define. It's called minimum variance unbiased estimator, MVUE. You will hear this term in estimation theory a lot. This is called minimum variance unbiased estimator. This is a class of estimator. It's a class of unbiased estimators with the lowest variance. Right? Sometimes people, sometimes they are referred as unbiased estimators that achieve CRLB, Cramer Rao lower bound. Remember I said Cramer Rao lower bound is the lower bound for the variance of estimator. But sometimes Cramer Rao lower bound is not achievable. So MVUE are the class of estimators that are unbiased first, because this is unbiased, right? And they achieve the lowest variance among all other unbiased estimators. So class of unbiased estimator with the lowest variance among other unbiased estimator. Good. So that was just the terminology. Now, something that I wanted to talk about that is very well-known concepts in machine learning and in statistics in general is very popular actually concept. It's called bias variance tradeoff. Bias variance tradeoff. What is this? So the idea of a bias variance tradeoff is as follows: that you can write the MSE, mean square error. Remember the concept of MMSE and the MSE, we talk about that, right? We talk about the fact that residual is equal to theta minus theta hat, and then MSE is equal to expected value of residual square. So we are all master of this stuff now, right? That the MSE, this is called MSE. MSE can be represented as, let's see, as what? Without spoiling it, I'm going to drive that one. See how easy you can drive it. Just expand this expression. Theta square plus theta hat square minus 2 theta theta hat. Remember, theta is a true parameter. Theta is true parameter. Theta hat is our estimator. Now, this is going to be expected value of, this is going to be theta hat, theta square. I don't need to write this value. Right, this is equal to this minus 2 theta expected value of theta. Good. Let's see how I can massage this equation to get something more interesting. If I go ahead and write this one as follows, write this expression as follows: theta minus expected value of theta hat square. Let's see what I get. I got theta square plus expected value of a theta square, so I can write this one expected value of theta hat square minus 2 theta expected value of theta hat. So this one we have. All we need to do is just subtract this extra term. Right? Let me write it better instead. Good. Let's not this equation for a while. Let's see what we get. We know MSE is equal to, what is this term? Let's go up. Look at this, what I defined here. I just said that E of theta hat minus theta is equal to bias. Right? So this is, since they are squaring that, doesn't really matter. So this is equal to bias square plus, this is nothing but just a variance. Expected value of theta hat square minus expected value of theta hat square plus variance of theta hat. Look at this. It says that MSE, mean square error, is equivalent to bias square plus variance of theta hat. So immediately, let's talk about this equation a little bit. If you have MV, minimum variance, unbiased estimator, then bias of theta hat is equal to 0. It says unbiased itself. Therefore, MSE is equal to variance of theta. That's one thing. Now, let's look at another interesting point here. If you let MSE to be fixed, if you hold MSE constant, then reducing variance or bias will increase bias or variance. What does this statement say that if MSE is constant, if you leave it as if you fix that, if you hold the value constant, then if you increase the bias, the variance should go down, right? That's hence the word trade-off. This is why it's called trade-off, bias variance trade-off. Now, if you increase the variance, the bias should go down because the MSE is constant, so it should add up to the same term, right? Good. Now, another point I want to make about this one. When you say when class of estimators with the lowest class of unbiased estimator, class of unbiased estimator with lowest variance is called MVUE, but class of estimators with smallest MSE are the MMSE estimators. I will write Bayesian estimators with quadratic cost. Good. Okay, so these are the properties that I want to talk about. That bias, Cramer Rao lower bound, consistency, definition of MVUE, and bias variance trade-off. The next video, I want to solve an example. I want to find the estimator from scratch and then check all these properties to show you how you can actually find these properties. And you can check whether the estimator is biased, unbiased, consistent or not. Now, like always, if you like this video, please subscribe to the channel, like and share the video. And I have written an article about the essential parameter estimation. I have all this stuff that I'm writing in that article with actually more explanation, some graphical explanation. And I will put a link to that article in the description. Thank you so much for listening. See you guys all in the next video.